Assalamualaikum and hi, my name is Nur Ayunusna binti Kamal Zaman, and today my group and I are going to present chapter 8, which is Physics Laboratory. So the presenter for today's are Nur Najha binti Hamidi and me myself, then Nur Afifah binti Muhammad, Nur Shuhaida binti Muhammad Hazrami and Wan Nur Hazwani binti Wan Azmi. So the learning outcome that we can learn from today's chapter, which is general safety practices, the students' responsibilities, electrical device and connectors, use and hazards of lasers, and model rocket launchers on school site. So next, I will pass to Afifah to share general introduction about today's chapter.
Hello, my name is Nur Afifah. To start our presentation, I will introduce you to the physics laboratory. A physics laboratory is a place where experimental physics is conducted. A physics lab is a place where it helps the student establish the relevance of the theories that they learn during class, such as electromagnet, relativity, and Newton's law of motion. Experimenting in the laboratory can clarify the student's mind regarding the subject's basic concept. After entering the lab, students can differentiate between theory and application. The physics laboratory helps a student improvise their approach to the topic. The physics laboratory also enables students to learn physics theory more elaboratively with the involvement of its application. Before we go further into our topic, we need to know the safety practice during the laboratory session. Firstly, the multiple plug shall not be used. Multiple plugs can cause an electric shock. Overloading and extension lead by plugging in appliances together will exceed the minimum current rating for the extension lead. This could cause the plug in the socket to overheat and possibly cause a fire. Then, avoid bringing both hands in contact when using an electric current. This minimizes the danger of an across the chest path for electric current. It is best if you can work with one hand when you work on with live power circuit. Other than that, the lab assistant or teacher must mark the induction coils with high voltage or low voltage. Students and teachers must also be cautious when handling acid or similar storage batteries. Batteries can be menacing when mishandled. These batteries are large and heavy objects that can cause severe injury if dropped, but battery acid is corrosive and can cause acute burn to skin or corrode equipment when it comes into contact with it. Lastly, students should know where is the emergency exit in the laboratory. It may seem simple, but it is essential to know where the emergency exit is. If we look at the surrounding, every building has an emergency exit. If an accident happens during the laboratory session, they know which direction they should go, so they will not be too panicked. All exit passages should be clear from anything that can hinder them from using and should not be locked when the laboratory is occupied. Now I will introduce you to some appliances that we always see or commonly used in a physics laboratory. First thing first, it is a voltmeter. A voltmeter is used to measure the electrical potential difference between 2 points in an electric circuit. There are two types of voltmeter, which are analog and digital. An analog voltmeter moves a pointer across a scale in proportion to the voltage of the circuit, while digital voltmeter give a numerical display of voltage. The second one is an ammeter. An ammeter is an apparatus used to measure the current, either direct or alternating electric current in a circuit. Then Ohm law apparatus, where we use to experiment with the Ohm law. The apparatus consists of one wire wall rheostat, one moving coil voltmeter, and one moving coil ammeter mounted on a backlight plate in a wooden case. It has 4 terminals, 2 for battery connection and 2 for resistant coil. We also use a spring constant to know about the hook law. It consists of a retort stand on which a spring is clamped onto it. Parallelogram to measure force acting on a single point. It consists of a small blackboard with two aluminium pulleys clamped at the top. Lastly, a sonometer measures a relationship between the frequency of the sound produced by a plug string and the tension length and mass per unit length of the string.
Thank you, Afifa. Now, before I start, my name is Nur Ayunusna binti Kamaruzaman, and I will talk about the student responsibility in the laboratory. So, each students have their own responsibility while conducting an experiment in the laboratory. When conducting an experiment, either in physics, chemistry, or biology laboratory, students especially need to follow all the safety steps. If student not following the safety step while in the laboratory, it will cause certain type of accidents. This because experimenting can be somewhat dangerous if crucial safety precautions are not taken. Before student conducting an experiment, we as a teacher need to give advanced and specific guidance for each experiment, including information about the equipment and materials used and any required or special handling that students need to follow in order to make sure everyone is safe inside the lab. Besides, students should know the lab procedure or understanding the manual of the experiment before starting any physical experiment. And now I will talk about the student safety practices while in the laboratory. So the first one, students need to wear proper safety equipment, which is PPE as instructed by the teacher. For example, like glove, goggle, lab coat, or apron. So PPE actually helps to avoid and protect students from any danger while in the physics laboratory, namely electric shock or laser beam. So this is why students need to avoid using defect PPE such as broken goggle or torn glove because they are no longer resistant to any hazard or maybe can only cause more harm to the users, especially students. For example, if we use scratch goggle, it may affect visibility and cause strain to the eye because it fails to serve their protective purpose. Thus, PPE should be used properly whenever necessary. And now we have the type of eye and face protection. So the first one is safety glasses. It used to protect against moderate impacts from particle, and next is goggle, which is it used to protect eyes and facial area immediately surrounding the eye from impact, dust or splash. And then we have face shield, which is it protect face from nuisance dust and potential splash or spray of hazardous liquids. And face shield is used for face protection, not the eye protection. If you want to protect your eye, you need to wear safety glasses or goggle under face shield. And lastly is laser safety goggle, which is provide protection from hazards such as ultraviolet light, laser and welding. And we also have type of glove, which is anti-vibrations, cut resistant, leader pump, chemical resistant, and also heat resistant. And now the second one of student safety practices in laboratory is before you leave in the lab or before you handling your personal items, if you wear a glove, you need to remove your glove and place it in the right place. And don't forget to wash your hand first properly, especially for those who involving the use of chemical or radioactive substances while in the lab. You need to make sure you are totally clean yourself. And next we go to how you doffing your chemical resistant glove. So the first one, you need to pinch and hold the outside of the glove near the wrist area, and you pull downward away from the wrist, turning the glove inside out like in the picture you can see, and then you pull the glove away until it is removed from the hand. and while holding the inside out glove with the glove hand, and then you continue to pull the glove down and over the inside out glove being held in your glove hand, and you pull downward away from the wrist, turning the glove inside out, and with your ungloved hand slide your finger under the wrist of the remaining glove and make sure you do not touch the outer surface of the glove with your bare hand because it is exposed to chemical. And next we go to how you wash your hands after doing the experiment. So the first one, you need to make sure you wet your hand with clean running water and apply soap on palm in circular motions. And then you rub soap on back of both hands and also between finger and fingertips. And then apply soap on both thumbs and rub it in a half circle for both hands. And then rub fingertip on palm, and then rinse hand slowly with clean water, and you wipe hand with clean and dry paper towel. And now the third student safety practice is you need to wear closed-toe and closed-heel shoes in order to protect yourself from any harm that exists on the floor, such as sharp object, hot, wet or slippery floor. So actually sandal and open-toe shoes do not protect your feet from broken glass that is frequently found in the lab. So you need to wear a proper shoes in order to enter the lab. Like in this example here, we can see that this person, she wear closed-toe shoes, but her skin is exposed. So this kind of shoes are not allowed to enter the lab. And the second one, we can see that this person, she added sock to cover her skin, but it only offer minimal protections to your leg. And the same goes to the third one, which she cover her entire leg, but she wear a fabric boots, which also will give you or will offer you minimal protections. So the best way is you need to wear a leather shoes that cover the entire top of the foot. And if you not wear the proper shoes, your leg will exposed to chemical like acid, and like in the picture here we can see that her leg is totally burned out with acid. The next student safety practice is you need to wear clothing that covers the legs, arm and torso, and do not wear legging or yoga pants because they offer no barrier between you and the chemical you working with. So the chemical can easily absorb and contact the skin. And next, do not wear synthetic fiber because synthetic fiber are generally quite flammable. And make sure you remove your loose clothing and jewelry and tie back your long hair. If you free hair, you need to tie up your hair to the back neatly and roll up your long sleeve, thus it will not get in fire or acid while doing the experiment. And it's the best not to wear any jewelry while in the lab because chemicals can become trapped under the jewelry and cause injuries to the skin, and jewelry also can conduct electricity, so it's quite dangerous. And the last one is you should never apply makeup, eat, drink or chew gum in the laboratory. This because within the laboratory where teaching and experimenting involving toxic substances take place can result in the accidental ingestion of hazardous material such as chemical, biological and also radiological. So cosmetic products also have potential to absorb chemical vapor and dust, and applying cosmetic in the lab, for example like hand lotion, also enable chemical absorption, and it is another source of skin exposure, particularly in the areas where hazardous chemicals are stored. And now before we go to the next part, I will show you the video of student safety practice in the physics laboratory. So I hope you guys will enjoy it.
I can fly. I believe I can touch the sky.
Now it's my turn to explain about my subtopic, which is electrical devices and connectors. There are a few subtopics under this part, which are: what is the definition of electrical devices, basic commands of electrical devices and connectors, what is electrical hazard, things you need to know about electrical shock, and the last one is the electrical safety measures and precaution in the laboratory. What is the definition of electrical device? Electrical device is defined as the device which uses the electrical energy for performing the work, which convert the electrical energy into the other forms of energy. For example, the electric bulb or tube light convert the current into the light. The electrical device mainly work on the high alternating current. Firstly, let me explain about some basic common of electrical device and connectors that usually found in the physics laboratory. The first one is the function generator. This function generator produces signals for other electrical equipments that need an excitation or drive voltage. The output of this generator is connected to the circuit or equipment using cable, usually BNC connector is used at one end while alligator clips are at the other end for easy connection to a circuit. Next is the DC power supply. It is used to provide voltage or current to operate other electrical equipments. Most single output DC power supply have three terminals, which are consist of plus, minus and ground. The last one is the variable auto transformer, or also known as variac. It is used to either step up or down the alternating current voltage, or also known as AC. This electrical device is useful in application requiring for non-standard voltage or where the voltage must be varied. Remember that this transformer does not provide electrical isolation, so avoid touching the output at any setting. Now, what is electrical hazard? According to the Occupational Safety and Health Administration (OSHA), electrical hazard can be defined as a serious workplace hazard that exposes people to burn, electrocution, electrical shock, flash or blast, fire and explosion. Now we are going to learn about electrical shock. For your information, even small electric currents through the body may cause death by heart failure. It is the amount of current flowing through the body that determines the effect on the body. Any amount of current over 0.01 ampere or so on is capable of producing a severe shock, and the current that exceeds 0.03 ampere is definitely lethal, which means can lead to fatal. Since the voltage at the outlet in the laboratory is usually fixed, such as 220 volt, the current that passes through the body is basically determined by the resistance of human body. The actual resistance varies according to some factors. such as the point of contact, the moisture content of the skin, and the voltage of the live part. Other than that, when in wet condition, skin resistance can be reduced directly. Therefore, this greatly increases the chance of severe electrical shock. Now, let's watch a video how to do first aid in case of an electrical shock happen.
An electrical shock may cause burns or cause internal damages or even can be fatal. Don't touch the injured person if he or she is still in contact with the current. Take these actions immediately while waiting for medical help. Turn off the source of electricity or move it away using a dry, non-conducting object. Call emergency if the injured person experiences severe burns, difficulty breathing, irregular heartbeat, muscle spasms, seizures, loss of consciousness. Begin CPR if the person shows no sign of circulation, such as breathing, coughing, or movement. Apply a bandage. Don't use a blanket or towel. Electric shocks can be fatal, so seek help at the earliest.
Next, we will be focused on the safety measures and precaution when using electrical appliance. The first one is to make sure our hands are dry when working with the electrical equipment or device. This is because wet skin has a lower resistance and it will allow higher and more dangerous amounts of current to pass through. Remember, do not carry out electrical experiment or use electrical device near water sources such as sinks, wet floors, and also bench surface. For safety, it is recommended to stand on an electrically insulating surface such as rubber mat or carpet when working with the electrical equipment to increase the resistance of the pathway from the electric source through your body. The second one is the flammable liquids should not be stored near electrical equipment because their vapor can be ignited by an electric arc or a spark. The third one is all electrical equipment used should be approved by a recognized authority such as Underwriters Laboratory, also known as UL, which testing product, design safety standard, and certified manufacturers. The fourth one is to ensure that the voltage rating of an electrical appliance matches with the voltage of the power supply before use. Other than that, always make sure that the student aware of the appropriate use of electrical device before starting the experiment and dangers of misusing them. The sixth one is the teacher in charge or lab assistant are responsible to know where the master switch of electricity in the laboratory in case of an emergency. Next is to remove all the conductive or metallic jewelry before working with electrical device. And last but not least, before using batteries, always check them first and avoid any present or cracks or leaking. Discard in a proper way if any of these conditions occur and inform the lab assistant for further action. That's all from me. Next subtopic will be presented by Wan Nurul Hazwani.
Assalamualaikum and hi. Before I start my presentation, let me introduce myself first. My name is Wan Nurul Hazwani binti Wan Azmi and I'm going to present about use and hazards of laser. A laser is a device that generates a very intense light beam which is either visible or invisible. Laser light differs from usual white light sources due to three primary characteristics. Laser light is monochromatic, means that laser light consists of a single wavelength, coherent with light waves moving in the same direction, and in phase and directional that has very little beam divergence. Lasers are comprised of four main components, which are lasing medium, thumb source, optical cavity, and output coupler. Laser light is particularly suitable for optical work. Helium neon gas lasers used in schools and colleges have a wavelength of 633 nanometer. Laser lines and laser pointers can also be used, but check that they are class 2 permitted for use in schools and colleges. Laser pointers tend to need new batteries quite often when used for experiments rather than pointing. Schools should only use class 1 or class 2 lasers for teaching purposes. If teachers wish to use a laser pointer in presentation, it would be safer to use a class 2 or lower laser pointer, as class 3R laser beam from such pointers may lead to damage of the eyes if viewed directly. Such pointers should not be used. Another requirements need to have when operating lasers in the lab is appointed a graduate science teacher to be responsible for the procurement, storage, issue and return of lasers and associated safety equipment, as they have knowledge how they handle laser without cause to hazard. And the last requirement is any person using the laser should be familiar with its operation procedures and the safety precautions.
Demonstrating optical phenomena in the classroom can be difficult. The trouble is, light beams are invisible. The normal scattering agents such as chalk dust are messy and can cause other problems in the classroom. The laser viewing tank allows students to see and manipulate light beams in a lab group setting. These tanks act as student workstations, so you can set up a bunch with little time or fuss. When I aim a laser into the tank filled with pure water, the beam can barely be seen. When I add a small amount of scattering agent to the water, the beam becomes highly visible. Some light is reflected from the agent's particles as the beam passes through the water. But we're going to dim the lights so you can see what's happening. Next, I'm going to aim the laser down toward the water at an angle to see refraction in action. Look how the direction of the beam changes when it enters the water. Set the tank at the edge of the table and aim the beam upward to see refraction again. If you increase the angle of incidence by aiming the beam through the water from the side of the tank, you will observe total internal reflection. When a source of white light is sent through the tank, the light appears blue from the side because the short blue wavelengths are scattered more than any other. Looking through the end of the tank, the light appears to have a reddish tint because all of the blue wavelengths have been filtered out through scattering. You can also use diffraction gratings with different numbers of lines to observe interference patterns. Look at the well-defined maxima. There are so many characteristics to explore. Students really have a great time exploring the phenomena of waves with this tank. It really makes science fun.
Classifications of laser are specified in the International Electrotechnical Commission and American National Standards Institute. International Electrotechnical Commission is applicable for safety of laser products emitting laser radiation in the wavelength range 180 nanometer to 1 millimeter. This type of laser products may consist of a single laser with or without a separate power supply, or may incorporate one or more lasers in a complex optical, electrical, or mechanical system. American National Standards Institute sets recommended guidelines for the safe use of lasers that operate at wavelengths between 180 nanometer and 1000 millimeter. The standards specify both of the environment in which the laser is being used and any environment around the path of the beam. While susceptibility to damage of materials is an important consideration with laser operations, the primary concern is the hazard to any person operating the equipment. International Electrotechnical Commission and American National Standards Institute classify each type of laser by its potential for biological harm. These classifications are Class 1, Class 1M, Class 2, Class 2M, Class 3R, Class 3B, and Class 4. The term eye-safe may only be used for Class 1 laser products. The term eye-safe laser should not be used to describe a laser based solely on its output wavelength being greater than 1400 nanometer. Lasers of any wavelength with sufficient output power can cause injury. Class 1 is a laser product that are safe during use, including long-term direct intra-beam viewing, even when exposure occurs while using telescopic optics. Class 1 also includes high-power lasers that are fully enclosed so that no potentially hazardous radiation is accessible during use. Intra-beam viewing of Class 1 laser products which emit visible radiant energy may still produce dazzling visual effects, particularly in low ambient light. Moreover, for the Class 1M, any laser product in the wavelength range from 300, 2000 and 500 nanometer to 4000 nanometer that are safe, including long-term direct intra-beam viewing for the naked eye. The MPE can be exceeded and eye injury may occur following exposure with telescopic optics. The wavelength region for Class 1M lasers is restricted to the spectral region, where most glass optical materials used in optical instruments can significantly transmit. Intra-beam viewing of Class 1M laser products which emit visible radiant energy may still produce dazzling visual effects, particularly in low ambient light. Let's take a look at the Class 2. In this class, laser products that emit visible radiation in the wavelength range from 400 nanometer to 700 nanometer that are safe for momentary exposure but can be hazardous for deliberate staring into the beam. Moreover, the use of optical instruments does not increase the risk of ocular injury. However, dazzle, flash blindness, and afterimage may be caused by a beam from a Class 2 laser product, particularly under low ambient light conditions. This may have an indirect general safety implications resulting from temporary disturbance of vision or from stator reactions. So, from the Class 2, users are instructed by labeling not to stare into the beam. Moreover, for the Class 2M, any laser product in the wavelength range from 400 nanometer to 700 nanometer that emit visible laser beams and are safe for short-term exposure only for the naked eye. The MPE can be exceeded and eye injury may occur following exposure with telescopic optics, such as binoculars. However, the effect of exposure to the beam like the Class 2, which is the users can get dazzle, flash blindness, and afterimage that may be caused by a beam. Users are instructed by labeling not to stare into the beam and exposed to the telescopic optical instruments. Class 3R consists of laser products that emit radiation that can exceed the MPE under direct intra-beam viewing, but the risk of injury in most cases is relatively low. Because of the lower risk, fewer manufacturing requirements and control measures for the user applied than for Class 3B, while Class 3R laser products are not considered intrinsically safe, but the risk is limited because unintentional exposures would rarely reflect worst-case conditions of beam, alignment with a large pupil, and worst-case accommodation with the entire beam energy entering the eye. The risk of the injury increase with exposure duration, and exposure may be hazardous for ocular exposure under worst-case conditions or for intentional direct intra-beam viewing. Due to the varying range of the risk that is associated with Class 3R lasers, the applicability of specific user control should be clearly described in the user instructions. Dazzle, flash blindness, and afterimages may be caused by a beam from a Class 3R laser product in the visible wavelength range, particularly under low ambient light conditions. This may have indirect general safety implications resulting from temporary disturbance of vision or from stator reactions. So from here, Class 3R lasers should only be used where direct intra-beam viewing is unlikely. For For the class 3B laser products that are normally hazardous when intrabeam ocular exposure occurs, including accidental short-time exposure, viewing diffuse reflections is normally safe. Class 3B lasers, which approach the AEL for Class 3B, may produce minor skin injuries or even pose a risk of igniting flammable materials. However, this is only likely if the beam has a small diameter or is focused. Lastly, for the Class 4 laser product, which intrabeam viewing and skin exposure is hazardous, and for which the viewing of diffuse reflections may be hazardous. These lasers also often represent a fire hazard. The eye that has been damaged by laser light, the first symptoms can be bright flash of light, if a visible wavelength, followed by a watering of the eye, headache, and floaters. Floaters are dead cells that have detached from the retina and choroid. If the cornea has been damaged, there will be a sensation of giddiness, as if sand were in the eye. In some cases, there may be immediate pain at the site of exposure. Let's move on to the next slide. Firstly, in the ultraviolet C and ultraviolet B that has the wavelength from 100 to 350 nanometer range, injury can produce photokeratitis, or known as welder's flash. This damage to the cornea that can be painful and usually repair itself within 24 hours. For the ultraviolet A that has the wavelength from 350 to 400 nanometer range, most of the light energy is absorbed in the lens, where damage can result in cataracts. In the visible wavelength from 400 to 700 nanometer and infrared A wavelength from 700 to 1400 nanometer range, severe damage can occur to the retina due to the focusing effect of the cornea and lens. Damage from light in the infrared A range, however, will not be affected by the aversion reflex, since the eye cannot perceive light at those wavelengths. Lastly, in the infrared B and infrared C range, laser light can result in damage to the cornea. Damage to the skin. The chance for skin exposure from lasers is greater due to the skin's greater surface area compared to the eye. Damage to the skin, however, is less serious. Different wavelengths of light penetrate to different depths of the skin, the most penetrating being from 700 to 1200 nanometer. It is possible to have a painful injury from a severe laser burn, but most skin injuries heal. Usually, a sensation of heat to the exposed area will be noticed, preventing most injuries. The exceptions to this are some high-powered lasers in the far IR range. The UVB range of lasers can be the most injurious, resulting not only in thermal damage but possibly in carcinogenesis. UVA can cause hyperpigmentation and erythema. UVC seems to have the least effect on the skin due to its short wavelength, which is absorbed by the epidermis, and infrared A, B, and C can cause the skin burn. The safety precaution when conducting lasers inside the lab are alert or exposure to laser beam. Students should be reminded that laser beams may lead to damage of the eye if viewed directly or indirectly. Some damage can lead to loss of eyesight. Next, never view the source of a laser beam directly, and no part of the skin should be exposed to the direct beam because it can cause damage to the eye and skin. No collimating instruments such as a telescope or microscope should be used to view the laser beam directly. Next safety precaution is use of protective equipment. Whenever possible, non-reflective or absorbing materials should be used in the vicinity of the laser to prevent specular mirror-like reflection. When reflection cannot be avoided, for example at a lens surface, position some protective screens so that students and teachers are not exposed to the reflection of the laser beam. Next, the protective screens should be made of non-flammable materials. They should be optically opaque and painted a matte gray color. Lastly, all persons who may enter or work in the laser area and liable to be exposed to laser radiation should wear appropriate protective goggles to avoid from the direct laser light into the eye.
Hello, I am Nur Najia binti Hamidi, and next I will be presenting about our last objective, which is the model rocket launching on school site. But before that, let's learn what is a model rocket first. Model rockets are a small rocket that are designed to be launched, recovered, and launched again safely. They generally don't contain any metal parts and only use certified commercial rocket engine to propel them upwards. These model rockets are categorized into low power and mid power rocket based on what engine motor it used. The history of model rocketry was started in 1954 by Orville and G. Harrison. It has become very popular after the World War II until now. So here, as you can see here, this is the structure of a model rocket. It has a body tube that keeps all the rocket pieces together, nose cone, shortcut, launch bed, recovery system, parachute, wedding engine, and lastly rocket fins to keep the model rocket flying straight. Okay, now how does this rocket work? Basically, if you look at this image, the motor will thrust up the rocket until the fuel inside the engine is completely burned and falling slowly with the help of parachute system, and it can be relaunched again after a new engine is inserted. So we will see a clear demonstration of rocket launching right after this, so stay tuned. Model rocket seems fun and simple, but it actually can be dangerous. Like if a recovery system fails, the rocket will come down like a giant dart that can pierce a roof of a car. This is why a rocket model launching really needs to follow the requirement and the safety precaution well. So, this is all the safety standard and precaution that we will discuss today, which is the authorization, well-planned plan, supervision, model rocket standard, and the launch site standard. Firstly, launching a model rocket in school site needs an authorization permit. At least 4 weeks before the date selected for the firing of the model rocket, the school needs to submit a firing request to the local fire protection agency. This special permit shall be obtained from the fire department for a given period, and if the permit is issued in the name of school administrator, the instructor must comply with all the safety standards of launching a model rocket. Next, the activities involving the firing must be well planned. The teacher should use prudent judgment and limit the number of launching, which is not more than 10 rockets if the students are present in the audience. And only authorized class and clubs may engage in this kind of activity. Supervision. The instructor in charge of the firing site shall supervise all the process involved in the rocket launching, including the disposal of unfired or defective rocket engine. If there is any misfire in the activity, please do not go after the rocket right after the misfire, and the rocket shall be allowed to remain in launch position for at least 1 full minute before it is approached. All disarming shall be performed under the supervision of the instructor in charge, and the person who checked the misfire also shall wear a face shield for safety. Now is the model rocket standard precaution, which is the size, the engine, and the launcher. Firstly, the size of the rocket. The length of the rocket must not measure less than 25 cm or more than 38 cm. The rocket shall contain no metal parts. Next, the engine. There is many types of engine, but in this activity, rocket with a smaller or class A engine are strongly recommended. Please never try to reuse or repack a solid rocket engine, as it is extremely dangerous. Next, the launcher. We need to launch a rocket from a launch rod that is pointed to 30 degrees of vertical to ensure that the rocket flies straight up. Also, the use of blast deflector is strongly recommended to prevent the motor at house from hitting the ground. Lastly is the launching at school site standard. So, the launch site hall must consist of firing area and also a recovery area. The firing area should be at the center of launch radius, and the firing must be within a radius of 25 feet or 8 meters from the location of the launching platform. For the recovery area, it must include the firing area and shall be determined to be the minimum area necessary for retrieval of the launch rocket. And the minimum size of the launch site is at least 30 meters of radius from the firing position. Next, the launch site also shall not be located at grain field, in area of dry grass, or in a forested area so that it does not pose any fire hazard. Not only that, we also need to avoid location near a high voltage line or major highway so that we will not distract any other people. now we have prepared a video demonstration of model rocket launching. So let's watch together.
Three, two, one.
In conjunction of this event, teachers hold a great responsibility and must caution students about the danger of experimenting with rockets and missiles, especially the dangers in preparing and use of non-commercial rockets and propellant. Using a non-certified rocket or attempt to make your own rocket engine is extremely dangerous, and according to NASA, there is actually cases where students are killed because they try to mix their own fuels. Therefore, it is really important for teachers to emphasize this to their students. Next, the propellant. Many propellant are highly toxic. Some propellant may burn spontaneously upon contact with air, organic matter, or certain cases it will burn suddenly upon contact with common metals. So, aside from caution the student, teachers must refrain from doing following practices such as providing chemicals for rocket, using or permit the liquid or solid fuels to be used in classroom, permitting the construction of rocket, and lastly, launching any other than commercial produced rocket engine of known size and predictable range. Now, let's look at the water rocket. In Malaysia, we often use water rocket for experimenting as it is more safer than model rocket that used propellant earlier. But safety is very important with any rocket, so let's learn a bit about the water rocket safety. A water rocket is a type of model rocket that uses water to produce the thrust needed to lift off. Water rocket is particularly not a toy. A pressured water rocket can store a huge amount of energy and fly 100 miles per hour. They can suddenly burst or injure bystanders. Therefore, students should never be allowed to launch water rocket without the concerned adult supervision. So it is the responsibility of all participants to be familiar with and follow all appropriate regulations related to the rocket. In water rocket safety, we need to use ordinary tap water, and we must not use substances that are harmful to the environment. So, for the materials, only lightweight, non-metallic external parts should be used so that the rocket does not conduct any electricity. Please do not use glass or any breakable container, and only use carbonated bottles that are designed to handle the emission of flight pressure. Next, the payload container has to be constructed from strong non-metallic materials and must be separate from any pressurized portion of the rocket. The payload section also should never include any flammable, explosive, or any biohazardous materials. Next, the pressure vessel and the pressure source. The pressure vessel shall be made of thin, ductile plastic capable of withstand the intense launch pressure and shall not use any metal. This is because not only metal is heavy and dangerous if dropped due to the failed use, but metal can also cause major problems if landed on power lines. Next, the pressure vessel may not be constructed using any portion of an existing high pressure enclosure. Pressure testing of all rocket pressure vessels should be performed by filling the vessel completely with water before pressuring the system. It is also recommended that a protection barrier be deployed to minimize the projectiles being ejected from the testing area if a burst of vessel occurs. Next, the pressure source. All valves, hoses, pipes, and fittings from the pressure source to the launch pad shall be rated for the planned launch pressure. The rocket must be pressurized with atmospheric air. No exotic gases, cryogenics, and combustibles are allowed. Next is recovery system. A recovery system is a part of rocket that allows the rocket to safely return to land after the launch. All model rockets that travels over 6 meters in altitude must have a recovery system that limits their descent rate at time of touchdown at ground level. So fault-boring rocket or any rocket parts can be very dangerous, so any recovery system malfunctions will disallow any record of flight. Example of recovery system includes parachute, steamer, gliders, and more. And the recovery system also cannot contain black powder or firewood. Lastly is the flight safety. Flight safety of the water rocket also same with the earlier model rocket that we discussed. A model rocket should be launched only outdoors in a clear open area without obstacles such as trees or power lines. Next, an audible countdown should be used before each launch. Rockets should be launched in safe weather conditions with wind speed no greater than 15 miles per hour. And next, do not attempt to recover any rocket from power lines, tall trees, or other dangerous places. And lastly, please do not launch rocket over or near a roadways.
Radioactive is something that exhibits or is caused by radioactivity. Radioactive emits radiation which usually forms electromagnetic wave or fast-moving elementary particles such as protons and neurons. Nuclear radiation can ionize chemicals within a body, changing how cells behave. Radiation can cause severe effects on the human body, such as can cause cataract, can cause cancer or burnt skin, and can cause sterility. Then we move to rules in handling radioactive. First of all, experiments involving radioactive material should be carefully planned. Planning an experiment will make us more familiar with the procedures, so there is a slight chance for mistakes during the experiment because we have prepared beforehand. Strictly, there are no demonstration of experiments involving radioactive. An experiment that uses radioactive should be done right away. Teachers and labs instructors should remind that the radioactive source must be small hazard so it does not pose an external risk to teachers and students. However, there is a specific way to store and label radioactive materials. All radioactive source should be kept in metal containers because metal is the preferred material for radiation shielding. Lead is highly effective in providing protection from source of radiation, so radiation material does not disperse into the environment. In addition, access to containers or rooms that contain radioactive must be limited. Only an authorized person, such as teachers and lab instructors, should be allowed. Metal containers should be permanently labeled and the label must be understandable for people to read. When a metal container is marked, it is much easier to identify each source of radioactive substance. This table shows the maximum amount of radioactive in stock. Cobalt-60, strontium-90, radium-226 and americium-2411 must be not more than 2 sources of each type, and each source must not exceed 200 kBq in activity. kBq is stand for kilobecquerel. 1 kBq is equal to 1000 BQ. Next, insoluble radium-226 source to be used with diffusion cloud chamber. The quantity that must be stored is not more than 10 sources. Each source of radioactive must be less than 70 BQ in an activity.
I can open up the container using forceps and making sure that I'm holding them at least 10 centimetres away. I carefully take the lead lid off the container, I lift it out, stand it on the lead lid. I use the radioactive source, ensuring I'm not pointing at myself or the pupils.
How far back should the students stand?
Well, as we can see, you're about 1.5 meters away, and the same should be true when you're doing this with your pupils. Ensure there's a good distance between where you're demonstrating it and where the students are standing. When I've finished, replace it back into the lead container, put the lead lid back on again, and ensure the source is back inside.
The most important thing is that the radioactives are kept secure, also that they're kept in a steel container so that in the event of a fire, the radioactive material would be contained safely within that.
If you'd like more information on handling radioactive sources, speak to your head of science or contact CLEEPS.
Next, I will continue about who can handle radioactive source at school. So actually, only appropriate, qualified or trained staff can handle radioactive source. So basically, teachers appointed to permanent positions on the science staff would be reasonably expected to have their qualification because they require to handle radiation risk, and so they need to have a sound understanding of associated hazard and staff handling requirements. Next, post-service teachers, temporary staff, or those whose science is a secondary subject, they may not be suitably qualified, so they need to be supervised by qualified teachers until they have considered gain knowledge and experience. And then laboratory support staff that have a range of qualification and experience. These laboratory staff should be comfortably dealing with radiations. So if school want to dispose the radioactive waste because they are no longer in safe conditions or they are no longer working or unsuitable for school, so they need to notify the radiation board secretary in writing within 48 hours or return back to the supplier. So this because based on Atomic Energy License Act 1984, no person shall dispose of or cause to be disposed or accumulate any radioactive waste without the prior authorization in writing of the appropriate authority. So this is why they need to notify the Radiation Board Secretary in order to dispose the waste. And also, radioactive salts used in the school lab is likely a very small amount of energy, so hazard from exposure to radiation is very low and small. However, people in the lab, whether students, teachers, or staff, need to take a careful step while handling the radioactive salts. And here are the example of radioactive salts, and also the package that radioactive salts need to be put, and the label that show the package contain the radioactive.
Okay, now we have learned about the safety practices for physics lab, use of equipment, and all the activity includes in the physics experiment. So, in conclusion, as the subject motto, remember safety first, I hope everyone does understand what we deliver to you today. Please do not take these safety practices for granted and let's create a fun and safe learning environment together.